Welcome to lecture 27 on memory interfacing and addressing. So, here what we will be seeing that till now we came to know that how a semiconductor memory is built, what are the technologies used. So, in this lecture we will see that we have a memory chip available to us, but we want to build a larger memory system. How we can do that? This is one thing we will be seeing in this lecture. Another thing that we will be looking into is that how we can further increase the speed of this memory. So, let us look into this. So, memory interfacing, here the basic problem is how we can do interface one or more memory modules to the processor. Here we assume that we have a single level memory at present. So, no cache memory. For the time being, let us assume this. The question that is to be answered here is how the processor address and data lines are connected to the memory modules, because now we are saying that we will not be having one single memory chip, rather multiple memory chips to make that memory. How the address and data lines from the processor will be connected to this. How are the addresses decoded? How the decoding of the address will take place? Because here you have to select an module and then select a address within that module. How are the memory addresses distributed among the memory modules? That also we will be looking into. And how to speed up data transfer rate between processor and memory. So, these are the four things that we will be seeing it in this lecture. So, as we know that memory for an n bit address bus, we can have 2 to the power n memory location and m data bus. We have read write and control signal. And now, this memory address register and memory buffer register connected through address and data lines to the primary memory. So, this is the processor's view of the memory, and of course, we have some control lines. Now, we will be seeing that now this primary memory or whatever memory we are talking about, we have set of some memories, and how those memories will now be connected with this address line and this data line. So, typical interface of the memory module, real chip may contain more signal lines. So, that is what we need to see. A note about this memory interface signal is that the data signal of the memory module are typically bidirectional. We have seen that the data bus is bidirectional, because from memory also data can be, some data can be passed through the data bus and written into memory, and from memory we read a data that comes to the data bus. So, it is bidirectional. Some of the memory chips may have separate data in and data out lines. So, some memory chips can even have separate data in and data out lines. So, for a memory read operation, what happens? The address of the memory location is applied to the address lines. So, in the address lines, the memory address location, address of that memory location is specified. Then for reading, the signal will be, this read write signal will be set to 1 and the chip select is set to 0. Data is read out through the data lines after memory access time delay. Similar way, for a write operation, the address of the memory location is applied to the address line. The data to be written, now I have to write a data into that memory location, that has to be written to put into data lines, and then this read write control signal is set to 0, because we have to write which is active 0, active low, and chip select is set to 0 again, because we are maybe selecting just that particular chip. So, why this chip select signal is required? See, it is not required if you have a single module. If you have a single module, you do not require a chip select. Chip select will be required only when you have multiple modules and you have to select one particular module from that multiple module. Then only we require chip select. What happens when chip select is 1? So, when this chip select line is 1, then the memory module is not selected and the data lines are set to high impedance state, that is, which is electronically disconnected. Let us see an example scenario. So, here is the chip select, here chip select is 0. So, this memory module is selected and here this chip select is 1. So, this memory module is not selected. Let us take an interfacing problem where we consider that so before taking an interfacing problem, I will take a small example to show how a larger memory is built from smaller memory. Let us take this example. In this example, we have to find out how many 128 cross 8 memory RAM chips are needed to provide a memory capacity of 2048 cross 8. So, I have to build a larger memory which is 2048 cross 8 and my available memory is 128 cross 8. How will I build it? So, basically all you need to do is that you will divide this by this and you will get the number of memory chips required to build that. That is coming to 2048 divided by cross 8 divided by 128 cross 8, you get 16. So, we require 16 chips to build a 2048 cross 8 memory. Now, 2048 is your total memory which is 2 to the power 11. So, we need to have 11 bits total in the memory address. So, the address bit will be 11. So, total address bit is A0 to A10. Now, each module you have a smaller chip which is 128 cross 8. So, this module is 128, that is 2 to the power 7. So, here you require 7 bits to select a particular row. So, once a particular row is selected, then this set of 8 bits can be transferred because one chip is 128 cross 8. So, the total address bit is now 11. How this total address bit will be divided? We have already seen that total address bit, now here it is 11, we need to select a particular row first. In this case, how many rows are there? How many chips are there in total? We have 16 total chips. So, we require a 4 cross 16 decoder to select a particular chip. So, the high order 4 bits, that is A10 to A7. So, the total address bit will be A10, A9, to A0. This is the total address bit 11. The high order 4 bits A10 to A7 will be connected to this decoder, 4 cross 16 decoder, that will select one of the 16 chips that is available. So, we have total 16 128 cross 8 starting from 0 to 15. Now, the output of this decoder is connected to all these chips, it is connected to all the chips. Now see, in the individual chip, how it is organized? It is organized as 128 cross 8. 128, so 2 to the power 7. So, the lower order 7 bits, that is A0 to A6, will be connected to all the chips. So, the lower order bits, that is A0 to A6, will be connected to all the chips. So, when we apply, we will first apply high order 4 bits. The total address is 11 bits. High order 4 bits will be applied to the decoder. It will decode and it will select any one of the chip. Let us say this particular chip is getting selected. Once this chip gets selected, then we have to select one location from this chip, one particular row from this particular chip, that will be A0 to A6. If it is the last location, then the value will be 1 1, 1 1, 1 1 and 1. So, it will be this particular chip and the last location, which is the location is 1 1 1 1 1 1 1, and a bit of 8 bit will be transferred through the data bus. So, this is the data bus connected here. So, this is how we can actually make a larger memory chip from a smaller memory module. We will take another example where we will see that we need a capacity of 2048 cross 16, and we have a chip which is 128 cross 8. So, we have a same 128 cross 8 and we need a memory capacity of this much. So, if you divide this by this, how many chips do you require? You will be requiring 32 chips. So, we require 32 128 cross 8 chip to build a memory capacity of 2048 cross 16. So, let us now see, again there are 11 bits in the address. How those 11 bits will be organized? In the same way, high order 4 bits will be connected to the decoder to select any one of the 16 chips, but we have a total of 32 chips. So, this decoder is now, see, it is connected to both the chips in the same row. So, this is a row. In this particular row, when I give 0 0 0 0, then this chip gets selected and also this chip gets selected simultaneously, because both are connected. Now, once we select this chip, now I will apply the lower order bits, that is A0 to A6. Now, I will be applying A0 to A6. When I apply A0 to A6, depending on the value of this bit, any one location from here and that same location, see, this address is going to all the chips here as well as here. So, whatever address we put in the lower order address bit, it goes to this particular chip and it goes to this particular chip as well. And then a group of 8 bits will be sent out to the data bus, the 16 bit. So, from here a group of 8 bits will come out, and from here a group of 8 bits will come out. So, this is how we can organize even larger memory from a smaller memory module. Now, let us take this a little bigger example. So, here we will consider a MIPS like processor with 32-bit address. Maximum memory that can be connected is 2 to the power 32, that is 4 gigabytes, and the assumption is that the processor data lines are 8-bit. Okay. So, remember this, the processor data line is 8-bit. Assume that the memory chips are available with size 1 gigabyte, and we need a maximum memory, we need to build a memory which is 4 gigabyte. So, roughly how many chips do we require? We will be requiring 4 chips. So, 1 gigabyte, so 30 address lines and 8 data lines. Giga is 2 to the power 30 and byte is 8 data lines. So, lower order 30 address line A0 to A29 are connected to the memory modules, and now we want to interface 4 such chips to the processor. Let us see how we can do this. So, total memory of 4 gigabytes we need to make. Let us see how we are doing here. So, we require 4 such chips, these are the 4 chips, and then the 30-bit address A0 to A30 is connected to all the memory modules. So, this address is connected to all the memory modules, and now what we are doing, we are taking 2 more extra bit, as I can only select any one of the chip at a time. I need to have a decoder. So, I need 2 more extra bits, that is 30 and 31. So, a 2 cross 4 decoder is required. Depending on these 2 values, any one of the following chips will get selected. So, if you want to select chip 0, CS0, then it has to be 00. If you want to select chip 1, it has to be 01 and so on. So, this is how it is organized, and at a time when we select a particular memory module, then a group of 8 bits will be transferred through this data bus to the processor. So, as I said, higher order address line A30 and A31 selects one of the memory modules. So, what happens when M0 gets selected? So, when M0 gets selected, the higher order address line will be 00. When this higher order address line is 00, then only memory module 0 is selected. So, what will be the range of address? So, the first address, this will be 00, it is a 32-bit address, these all are 30 bits and these 2 are 00. So, total 32 we can group it into 4 hexadecimal, and if we group it into 4 hexadecimal, so this 4 will constitute first, next and so on. So, what will be the range of address? So, as we know that this will be 00, first 2 bits will be 0 for all, and the address range will actually start from here. So, till this will be 00, 0000, and the last address will be this, last bit will be, this will be 00 because this is the 0th module, and this will be 1111. So, what will be the range? The range will be 0, 8 zeros to 3 7Fs. This will be the range for module 0. Similarly, for module 1, this will be 01. If this is 01, all will be 0 1s and all will be 1. So, if all is 0, then this will be 0 1 0 0, that is 4. First, this set of 4 bits will be 4. So, it will be 4 00000 to 7FFFFF. Similarly, when M2 is selected, it will be 8 7 zeros to B7F, and similarly when M3 is selected, it will be like this. So, the range of address will be like this. Let us see what observation we are getting. We can observe one thing, that the consecutive block of bytes are mapped to the same memory modules. So, the consecutive blocks are mapped to the same memory module. For MIPS, we have to access 32 bits, that is 4 bytes of data in parallel. So, to do that, we require 4 sequential memory accesses. Because it is 8 bits, so 1 by 1 by 1 we have to access it. Now, we shall look into an alternative memory organization if there is a way that we can do something such that all the modules can be selected once and then the data can be transferred. This is called memory interleaving. So, improved memory interfaces for MIPS 32. So, we make a very small change here. What is that small change? So, we organize this 32 bits of data that can be fetched in a single memory access. We exploit this concept of memory interleaving. The main change that we do here is that high order 30 address lines, that is A2 to A31, are connected to the memory modules, and the lower order 2 address lines, that is A0 and A1, are used to select one of the modules. Now, earlier the higher order bits were used to select the module. Now, we are using the lower order bits to use the module. So, what will happen? How the addresses will be mapped? So, in the module 0, it will be 0, 4, 8, 12, 16, 20 and 24. Module 1 will be 1, 5. So, a block of 4 words consecutive addresses are now mapped into separate modules. Now, in module 0, earlier we were having 0, 1, 2, 3, 4 like this. No, here we are having the consecutive words in consecutive modules. So, what advantage can we get if we have consecutive words in consecutive modules? If there is a way to select all the modules and then these data, we have a large enough data space that can transfer the data from all these modules simultaneously, then we can get 32-bit data at a time. So, this memory addresses are interleaved across the module, meaning first address of the memory is in module 0, the next address in next module, next address in next module, next address in next module. So, this is the way to represent, we call it interleaved, the memory addresses are interleaved across the memory modules. So, what we can gain from this mapping? As I said, if the consecutive addresses are mapped to consecutive module, then possibly we can access the 4 consecutive words in the same cycle, if all 4 modules are enabled simultaneously. Let us say all 4 modules are enabled simultaneously. So, from this address you can access the word, from next address, from next address, from next address. So, all 4 words which are there in this 4 different modules can be accessed together. So, now we can see the motivation for this word alignment in MIPS data word. If the words are not aligned, what can happen? See, the 32-bit word starts from a memory address that is divisible by 4. So, corresponding is 0, 1, 2, 3, 4, 5, 6, 7, all these. So, these are in different modules. Possible to transfer all the 4 bytes in a single memory access, because I will be hitting 4 different modules, and from 4 different modules I will be getting the data. What happens if the words are not aligned? Let us say some words are starting from 1, some words are starting from 2. Then what will happen? My words are in consecutive modules. So, 1, 2, 3 and 4, but I require this will not help us, this is not aligned because it is not starting from 0. So, in that case I need 0 as well. So, to do that, in one memory access I can get this, and in another memory access I also need to get this 0th location. Hence, the word cannot be transferred in single memory access. It will be accessed in a single memory access only, single memory cycle only if when it is aligned. If it is not aligned, it will require more number of memory access. In this case, 2 memory cycles will be required. Now, let us see what we are saying. So, the higher order bits are connected to the address modules, and the lower order bit is connected to the decoder. It is still connected to the decoder, and through this decoder at a time one of the memory module gets selected. Once one of the memory module gets selected, then 8 bit of data is transferred. So, a bottleneck still exists that we have a data bus of 8 bit. Still one module is selected at a time, and 8 bits data transfer per cycle is taking place. Now, let us say all modules are selected, at all times. And one more change we have done, we have made this data bus as 32 bit, and the high order address is connected to all the memory modules. In all the memory modules, the high order address is connected. So, in this case, what will happen? As all the modules are selected, whenever we give that address, first address, then the data from all the 4 modules get selected, and it will be transferred to this 32 bit data bus. So, from this module 8 bit will come, from this, and then it will be transferred to this 32 bit data bus to the processor. So, the advantage we get here is that all the modules are selected, and we apply a same address to get different data from different modules. It would not have been possible if the addresses are consecutively in a single module. It is only possible because the addresses are interleaved across the modules. So, it enables all 4 modules together. So, 32 bit parallel data transfer is possible. We already discussed about this regarding memory latency and bandwidth. So, we will take a small example to explain this. What is latency? Latency is the delay from the issue of the memory read request to the first byte of data becoming available. So, it is the time required to access the first data, and then consecutive data can be accessed in a much quicker time. What is memory bandwidth? The memory bandwidth is the maximum number of bytes that can be transferred between the processor and the memory system per unit time. Per unit time, maximum number of bytes that can be transferred between processor and memory is termed as bandwidth. Let us consider this example. So, here a memory system takes 20 nanosecond to service the access of a single 32 bit word. So, that means 20 nanosecond is the latency. In 20 nanosecond, it is transferring a single 32-bit word. What will be the bandwidth? Bandwidth will be 32 divided by 20 into 10 to the power 9. So, latency is already given. So, you can just see this, that latency is 20 nanosecond, 20 into 10 to the power 9. And what is how many bits of data? 32. So, 32 divided by 20 into 10 to the power 9 bits per second. This is the bandwidth. So, you can just do the simple calculation, which is coming down to 1600 into 10 to the power 6 bits per second, and it will be 1600 megabits per second. Finally, if you divide it by 8, you will get 200 megabytes per second. So, the bandwidth is 200 megabytes per second. Let us take another example. Here the memory system is little bit modified to accept a new, still this 20 nanosecond request for a 32-bit word every 5 nanosecond by overlapping the request. Now, the next word is overlapped. That means, every 5 nanosecond the next word is available. So, how we can change this? So, the latency will be still 20 nanosecond per word. So, there is no change there, but now the bandwidth can be increased, because after every 5 nanosecond the next word is available. So, it is 32 divided by 5 into 10 to the power minus 9, which is coming down to 800 megabytes per second. So, we have seen some of the examples and what is latency and bandwidth and how are they important in the context of memory system design. So, now we came to the end of lecture 27 and we have completed memory system design to some extent. Next, in the next lecture, we will be looking into how we can further make the memory faster. So, we will be moving on with the memory hierarchy, cache memory, virtual memory, etc. Thank you.